Welcome back to the Pathfinder's Codex, where we're doing some exploratory programming to learn new things. Let's implement Newtonian gravity on a graphics card and learn some new techniques that you can apply to your Godot projects. Here's the fun prototype that you can download and try yourself. Introducing the Dancing Dots 2D Star System Particle Shader. In this video, I'll walk you through the hobby project, visualize what's going on, and we'll check out some of the code that you might want to modify and experiment with. In the version I cover today, we won't use any fancy algorithms, maybe another day. Instead, we'll use the tried and true pairwise comparison method, where we cross-check every dot in the sim with every other dot, and we'll do that every frame. We could do this on the CPU using basic nested loops, but that would quickly become a slow and choppy mess even with a modest number of dots, so we'll move the heavy computation to a compute shader. Our goal is to create a fun and visually compelling result, and so we're going to be cutting some corners on how optimized and accurate it'll be. At the end, we'll look at some of those shortcomings and cover some of the areas of the code that can be improved on. Before we begin, here are some of the techniques and topics covered in the video. We'll walk through a compute shader in Godot that runs over 2 passes each frame. It'll resolve the physics in the first pass and then draw the texture on the second pass. In the shader, for the first pass, we'll implement a basic particle gravity sim based on Newton's laws. And we'll have the dots collide and merge based on simple circle collision detection. When the shader goes to draw the image in the second pass, we'll manually rasterize the circles, giving us the different sizes and colors of the dots based on their mass. In the UI, we'll be adding a small subviewport for a zoom window, sort of like a mini-map. We'll attach the zoom center to the mouse cursor so that the zoom follows the mouse position. And while we're doing all of that, we'll also implement a roll-your-own performance monitor and scrolling graph display to help us identify slow code and inefficiencies in our pipeline, the shader, and the project logic as a whole. More on that later. The project is surprisingly small and only contains a few important components. It contains 4 core scripts and just a handful of scene nodes that we need to know about. Let's start with the scene structure. Here are the most important nodes to give you the big picture. First is the Compute Galaxy Texture Rect node. This is where the image of the simulation will be displayed on the screen. It contains all of the logic to set up the shader and run it every frame. It's also where all of the parameters are found for the simulation. Things like gravity variables and the starting dots patterns. Then we have 2 subviewports. These branches of the scene tree allow us to quickly hide parts of the UI and to draw to different parts of the screen using independent viewports. The first is for the performance graph. We'll draw the timing graph data to this viewport to get a visual indication of performance in real time. Different data points will be different colors. The other viewport is used for the zoom window. This little window shows the zoomed out view of the image texture. We'll make the zoom focus on the mouse just because we can. For the UI, we're keeping it simple. A few labels, a slider to control the speed scale, and a few buttons. The buttons will toggle the performance graph and the zoom windows on and off. And the slider will allow us to change the speed of the simulation, even reverse the speed, although it can't undo merges. The code is broken down into 4 main scripts, 1 for the GLSL shader and 3 in GDScript. We're going to focus on the shader code in the second half of the video, so let's look at the GDScript parts first. The GD files are responsible for invoking the shader, handling the few UI controls that we have, and monitoring the time-critical parts of the code. In a moment, we'll look at the GDScript files in more detail, but for now, let's get a bird's eye view. First is the main.gd code, and it's not big at all. It connects up the UI button and slider elements using signal functions, and it also sets up the zoom viewport. Then we have the performance monitor and perfgraph.gd. This is the custom code for logging debug timing and drawing a scrolling graph using those data points. The last GDScript file, computegalaxy.gd, is the most important, as it's where we're going to set up the rendering device pipeline, configure it and invoke the shader in several passes, and handle the results of each compute frame. It's also where most of the fun configuration settings can be found that impact the simulation. Things like basic gravity parameters and the starting board for the dots. Before we jump further into the code, please take a moment to like and to subscribe. It means the world to us, and it helps the channel a lot. Okay, let's poke around some of the Compute Galaxy GDScript and see how it coordinates the shader pipeline and then executes the shader in 2 passes. There are a ton of configurable settings, and some are more useful than others, so let's focus in on a few important variables that we might want to experiment with or change. One of the biggest impacts to performance will be due to the time it takes to transfer the image texture from the GPU to the CPU each frame. And so we need to be careful how big we make this image. It's a fine line between how much of the simulation we can see at one time and how much of an FPS drag it becomes. So I generally leave this at 2048 and will sometimes lower it to 1024. We can adjust the strength of gravity by adjusting big G up or down. However, this can significantly change the velocities to become so fast that it's hard to see what's happening. And we'll see later how that can impact collision logic. There are a few different ways that we can set up the starting dots on the board. Most of them are configurable patterns, and so we have settings here to control things like how many dots we want and how big they should be. There are options for how big the center star is, how big the system is, and how many in the shape of the arms it should contain. Not all of these are used in every startup method. We'll look at the startup process in a minute. Because the dots can merge during the simulation, we'll see that over time we accumulate a bunch of useless dots that have no mass. But the shader still processes them anyway. So we'll use a series of pruning functions to help us determine when we should rebuild the entire system and leaving those empty dots out. This can reduce the workload on the GPU as the number of dots drops, at least to a certain level. Here we have some of the settings that allow us to control parts of that pruning process that happens on the CPU. Again, we'll see more on this in a second. Another setting worth looking at is the shader's local size. This isn't the actual local size, that's defined in the shader itself, but this setting allows us to control, at least in a roundabout way, the number of groups working on the GPU. Depending on your hardware, it might be important to change this. For now, I keep it at 512, though honestly I'm not sure what would be best. There are a bunch of other variables here that aren't meant to be changed, like those that hold the rendering objects, the uniforms, and the buffers. We'll see these in action in the next section, but if you want to know more about what they are, the Godot rendering server documentation, and especially the Chronos.org documentation, will be helpful. Okay, so that's a lot of moving pieces. Let's look and see how they come together to create our visuals. We'll start by initializing the playfield with a bunch of dots. Then, during each process tick of the simulation, we'll call the shader, handle the results, and prepare for the next frame. As with most code in Godot, we'll start in the ready function. We'll initialize a few things like the random seed, the speed scale, and the logging system. We'll also create an image format that our texture will use. Then it generates the starting pattern of dots, using one of a few different functions. I have it set to use a custom pattern, but this could be swapped out for another starter function if desired. For example, there's a function for a basic random spread of points along galactic arms, and a version that generates a more spiral-like random system. You could make your own startup methods too, and that's really what the custom function does. So let's look at how it generates the starting playfield. Each point in the sim has three main properties. These properties, the position, the velocity, and the mass, are stored in arrays within Godot. Not just any array will do though. We'll use packed byte arrays, which are highly optimized for storing large amounts of byte data. This makes the byte transfer to and from the GPU easier to manage, and it improves performance a bit. For now, our position and velocity data will be using packed vector2 arrays, because they both contain an x and y component. And our mass data will be stored in a packed float32 array, because it's a single floating point number. These typed arrays will be converted to packed byte arrays before being sent to the GPU. In the custom starter function, we're going to do it like this. First, we'll add the center object, the star. Best if we can keep this as the first dot in the list. Then, we'll add a few test case objects of different sizes and positions. This will let us test specific setups if we want. For now, we're just going to add a handful of larger dots. Now, the fun part is that we can still add one of those other starter functions like basic or spiral to add more dots. So here, in addition to creating the objects above, we're going to add an entire spiral pattern of dots to the list. You can change this out too, just like before, if we want to mix and match creation functions. When we're done generating the three arrays using the starter method, we'll pass the packed arrays to a rebuild buffers function. That'll set up the shader pipeline and build the buffers that the shader is going to use. Let's check out that function because it's used later as well. This function takes in three arrays and formats them into the correct buffers for our shader. It'll set up the shader and the pipeline objects. It'll format the input buffers for position, velocity, and mass, and it'll also set up output buffers for those arrays as well. The function then assigns the correct binding to each uniform, including the output texture that we want to draw to screen. The rebuild function finishes up by recreating the uniform set for the shader. With this function, we can recreate the points at any time, and it'll automatically set up the new buffers for us. Now that the buffers are initialized, we can focus on the main processing loop. We'll touch on the performance graph later. For now, we'll focus on the compute shader and the two passes that we make over the data. Every time we call the shader, we'll send several push constants, like the gravity constant, the speed scale, and the number of points in the system. You'll also notice the first push parameter is either a 0 or a 1. This is how we're identifying the run mode in the shader. Pass 1 will be run mode 0, and will tell the shader to run the physics logic on the incoming dots. Pass 2 will be run mode 1, and let the shader know to draw the dots to the output texture. Sure, we could have done this in a single pass, but I wanted to demonstrate how a two-pass shader might work. And later we could use this concept to improve our process by using more optimized passes for better parallel computing. Still, when these two passes are done executing, we'll have the data we need. So now it's time for the GDScript to resolve the results for this frame. Here's how the shader resolution works each frame. First, we grab the raw byte data from the 3 output buffers. These are where the shader wrote its results for each of the dots. Then we'll review that data and check if we need to prune it down. We'll see that in a second. For now, let's assume no pruning is needed. In that case, the script finishes the frame process by doing two things. It performs a buffer swap on all 3 arrays. It writes the new byte data that came from the output buffers back into the input buffers. This way, the next frame will always be working on the correct next step. And it finally grabs the texture output from the shader, creates an image out of it, and places it into our Godot scene. If there's no pruning for a frame, then that's the shader flow that happens during every process tick. Okay, what happens if we need to prune the list of dots? How do we know if we need to prune the points, and what does that really mean? The simulation handles merging 2 colliding dots by moving the mass from one to the other, and leaving the smaller mass at 0. It works, and it keeps things moving along, but the dots still have 0 mass and have a position and velocity which are taking up valuable space. And the shader needs to process those points even if they have 0 mass, and that has a performance impact. The goal during the pruning is to remove all of those 0 mass dots from the buffer arrays. Since the number of dots has a quadratic time complexity, the more dots we can remove, the faster the shader will run. But the process of pruning is pretty inefficient since it happens on the CPU. The counting of empty points and pruning the zeros out are pretty expensive operations, and so we need to make an informed decision on exactly how many empty points are acceptable. We can change the class variables to affect when that pruning happens. We'll use a function that checks the data for empty masses, and we'll count how many zeros there are. Once we have the number of empty points, we can choose whether or not to proceed with removing them. If the values exceed our configured thresholds for pruning, we'll proceed with the function that removes those zeros. That function uses a basic loop and recreates the data arrays without any empty dots. And most importantly, since we're changing the number of dots, we need to completely rebuild the buffers for the shader. Luckily, we already have that function, and we can just pass in our reduced data arrays that only have the massive objects. If we end up pruning the arrays, we also need to skip the buffer and image swap during this frame since the input and output buffers will be misaligned. So the pruning function returns a true or false, and we can use that to skip the result of the frame resolution. We have a bunch of moving pieces that can potentially be slow or problematic. To help identify areas of code that are costing us the most, we'll use a roll-your-own performance monitor to help us. It stores a queue of timing data points for each frame, that we can then draw them with different colors on a graph on a screen. You can see the debug boilerplate all over the place where we're starting and stopping the timers and giving them unique keys. The cost of this monitoring is actually pretty high because it was a quick solution. Simply having to redraw the graph every frame is slow with the current technique and needs some work. The drawing function for the performance graph is straightforward enough. Assuming the graph is turned on and visible, it'll draw up to the last 475 frames worth of timing points, to a subview that is apart from our main image. We can change the colors or comment out things we don't care about or have determined that are not a big time concern. One thing to keep in mind, besides the fact that the monitor itself has a major negative impact to overall FPS, is that we often find that it's the calling code that invokes the shader, or how we're copying, manipulating, or reading the buffer data that has the highest impact. Yes, the shader isn't perfectly optimized and can be slow with a large number of dots, but ultimately it's only a portion of the total time consumed in our frame rate. At least with this performance graph, we can try to narrow in on those areas that are costing us the most and might have simple solutions. We'll touch on some possible improvements for this at the end of the video. Now that you see how the GDScript calls the shader and handles its output, let's look at the compute passes in more detail. First, the high-level stuff, like the local size, our input and output buffers, the output image uniform, and our push constants. If you've followed along in our earlier shader videos or have read through the Godot documentation for using them, this should be familiar. We're going with a local size of 512 for now, but like I said before, I'm not sure where this should be. It has an impact in several different ways and is sometimes specific to different GPU hardware. We might even need to rethink it if we need to add more shader passes later on. Let me know in the comments if you have ideas or advice. The buffers will hold our particle data, and that includes both the input values and a place to put the output values. This image uniform is where we'll draw the pixels to. The CPU will read and display this image data after each frame. And here are the push constant parameters that we can change each frame. For now, we're sending only the basics like point count, gravity, and the timescale. Then there's the run mode push constant. This controls which logic runs in the shader. So when the GDScript passes in a run mode of 0, we're going to run the simulation logic. And when it passes in a 1, we're going to run in the drawing logic, which is how we've set up the shader's main entry function, as you can see here. Okay, now onto the chunky stuff. Let's look at each run mode to see what they do. The two run modes are executed one after the other, with the simulation running first, followed by the drawing logic. The simulation pass is definitely more complicated, so let's go over the drawing logic before we get to that. Here's what happens in the draw texture method. We want to draw our dots in different colors based on their size. So we'll grab the global invocation ID for the current dot we're processing, and use that to look up the mass for the dot. Since this is the second run mode to be called, we actually have two masses to work with for the dot. The previous mass before the simulation ran, and its current mass, if any. Using these values, we'll figure out how big the dot should be. The size of a dot is going to be based on its mass, but not linearly. We'll use the cube root of the mass, which gives us a more realistic size, almost as if it's an actual spherical planet. Just because a dot is twice as massive as another dot, doesn't mean that it's visually twice as big. Great, now we have the old size and the new size. Assuming the dot falls inside our draw boundary, and we actually have something to draw, we'll proceed with two things. We'll erase the previous dot by wiping out those old pixels, and we'll draw the new dot in its new location and size. Both of these drawing operations use the draw circle method. This helper function takes the dot's position, its radius, and a color, and draws the correct pixels using a simple nested loop. As we're looping, we'll make sure the pixel is within the radius for the dot center, and use the image store function to set that pixel's color. The colors we're using depend on if this is the erased circle or if it's the new dot being drawn. For the erased circles, we're overwriting the pixels with a transparent empty color. But for the actual dot's new position, we'll choose a color based on the mass of the dot. For now, we're using the center mass as a baseline, and if a dot is a certain percentage of that mass, it'll go up to the next dot color. I tried to pick colors here that match the tests I was doing. They seem to work well, and you have a satisfying progression of colors as the dots merge and get bigger. However, the percentages here highly depend on the total mass and density in the star system, so you might have to change these around if you want different effects. Nice! Now when the shader drawing mode executes, the image should reflect the new dots after the current frame. It's not perfect because of the way we're erasing old dots, but it works well enough and those inconsistencies are not a big deal. Now let's take a step back and look at the main simulation logic in run mode 0. This is where the magic happens, at least as far as the gravity physics and the merging logic. Here's what happens in the run sim method. It's important to note here that we're reading the values from the input buffers and writing our results to separate output buffers. We won't modify the incoming data and will only write to the output data. First, like in most single-dimensional shaders, we'll grab the global invocation ID. We'll use it to look up the position, the velocity, the mass, and the radius values for the current dot. We'll have a few scenarios where we don't want to continue processing a dot, and you'll see them in this function where they return early. If the dot is outside of our point count, or the dot doesn't have any mass, then we'll just skip it. If we don't skip the dot, we'll proceed with the gravity and the merge logic. The process we're using is a brute force nested loop method. It's a pairwise comparison that runs in quadratic time. What do those terms mean? Basically, we're going to take the current dot, and we're going to cross-check it against every other dot in the simulation. This can be referred to as a pairwise comparison. And since we're doing that loop for all dots in the simulation, as the number of dots goes up, the number of cross-checks we need to do will go up quadratically. That means if the number of dots doubles, the number of checks grows by a factor of 4. It's not exactly great for performance, but it works well enough with a reasonable number of dots. It's what we need to do to calculate the gravity forces, because even if the effect is trivially small, an object that's millions of miles or even light years from a dot still has a non-zero impact on that dot. We can improve this with more complex algorithms later on, but for now, we need to do these pairwise checks. So let's look at the pairwise loop. This loop represents the current dot being checked against every other dot. We're going to use three common Newtonian formulas to help us. First is Newton's gravity equation. Second is related to his laws of motion. We'll use it for conservation of momentum during collisions. And the third is also from his laws of motion, and it calculates acceleration for us. We'll see how all of these are used in a moment. Inside the loop, we'll first do a few sanity checks, making sure that we don't cross-check against ourselves, and that the other dot we're comparing it to isn't an empty dot. With that out of the way, we can determine our size and the other dot size. We'll also calculate how far apart we are. With our distance apart and the dot size is known, we can quickly figure out if we're colliding with the dot. If we're closer than the combined radius, we'll count that as a collision. We'll come back to the collision logic in a second. For now, let's focus on the gravity bits. Before we started the loop, we created an empty total force vector variable. We'll add to this vector every time we cross-check the current dot with another dot. As we're comparing each dot with the current dot, we'll figure out how much pull the other object has on us. Here's where the first important formula comes in. With Newton's law of universal gravity, we can find this pulling force. We'll normalize the force and add it to our total force variable, before moving on to compare the next dot. The expectation is that after we've compared this dot with all other dots, that total force should represent the combined gravity of all other objects in the system. With the big calculations out of the way, when the loop ends, we can finally figure out where to move the dot for the next frame. Using one of Newton's motion laws, we'll calculate the acceleration based on the total force from our earlier calculations. And we'll use that acceleration to determine our new position and velocity. We'll scale this movement by our dt push constant, allowing us to slow down or speed up the sim in real time. And finally, we write to the three output buffers, the new position, the new velocity, and the new mass. Those buffers will be available for the GDScript to read out after this frame runs. And that's it, we're done working on the current dot. Oh, wait. Let's go back and look at the collision merge logic. So it turns out that merging logic can be tough to tackle in parallel, at least without breaking the shader into more passes. Here's how we're currently handling it. A collision will only be resolved if it's the smaller dot that's running the pairwise loop. That should help prevent us from processing the same collision twice. We'll assume that when the larger dot is running its own loop, that it would also collide with this one, so the merge wouldn't be handled during that collision. To resolve a collision, we'll combine some of their values. The two dots' masses are simply added together, but the velocity is a little more involved. We'll use the formula for conservation of momentum, applied as an inelastic collision, to blend their velocity together based on their individual masses. To finalize the merge, the larger dot will absorb the smaller dot. We'll take our new totals and write them to the output buffers. And importantly, we'll zero out the smaller object's mass and velocity, essentially making it skippable in future shader frames. We exit early if we're the dot that got absorbed, otherwise we'll continue with our pairwise loop like normal. To recap, during each frame, when the shader calls run mode 0, the GPU will process the dots in the buffer, and each dot will run through this loop code. Maybe it'll be moved, maybe it'll grow in size, or maybe it'll be absorbed, but in any case the data is written to the output buffers for the next frame and the GDScript to use. That's immediately followed up with a run mode 1 where the dots are then drawn and pulled back to the CPU as a texture. That's how we did it anyway. When we put all of these things together, the GDScript and the OpenGL code, we get the final result. The GDScript handles setting up the pipeline, as well as executing the shader and resolving the results during each clock tick, while the shader itself does the heavy computations of the pairwise comparison, giving us the gravity and collision effects that we're looking for. I spent a lot of time trying different settings, different densities, starting configurations, different ways to merge objects, and even ways to count empty zeros. I'm impressed at how the results turned out so far, even though I know there's some obvious gaps and things that should be done differently. I mentioned at the start that there were some shortcuts that were taken to get to this point. You may have spotted a bunch of ways it could be improved already, and I'm sure there are obvious bugs that could be hammered out. The goal was never to have a perfect parallel process, but to have a good starting point for others to play with. Something documented in a way to make learning the overall structure easier to follow, and some tools that could be used to benchmark and monitor which parts are slow. Here are some of the gaps I've considered, roadblocks I've encountered, and things I'd do differently next time. These generally fell into three categories, first being hits to overall performance. The performance gaps revolved around a few different aspects of the project. The first one is the fact that we're doing pairwise comparisons. That works great for small or reasonable numbers of dots, but as the number of dots goes up, the processing time will quickly become unmanageable. There are advanced methods for solving gravity that don't use this brute force approach, such as Barnes-Hutt or fast multiple algorithms, but we're going to save those for another video. For now, we're just going to keep the number of dots below 200,000, It may be a little choppy at first, but as points are merged and pruned out, it should speed up to be visually appealing. Another issue, one that I didn't find an obvious solution to, was how large the image texture is that we read from the GPU every frame. It's not a fast operation and it has a consistent impact on the overall frame rate. What we found is that at some point, especially when the number of points is low enough, that this texture transfer actually takes more time than running the gravity shader. In general, there comes a point when maybe running in a compute shader is more detrimental than if we just did all these calculations on the CPU. As a possible way to reduce the pairwise comparison performance, we're using pruning. As the dots merge in the sim, they leave a bunch of dots with zero masses. And we can reduce the number of loops that the shader needs to perform by removing these. But we find that having to count the number of zeros, just so we can decide if we want to prune or not, is costing us. We may be able to improve this by having the shader perform a set of sum scans on the GPU, but for now we just left the logic on the CPU. The other part of this problem is when we finally decide that we need to prune the dots, we need to rebuild all 3 input buffers with the new data, minus those empty dots. That rebuild operation can be pretty expensive, but at least we're only doing it when we've hit the prune thresholds. Interestingly, the last performance hit comes from the performance monitor itself. The way we record timing data points isn't exactly optimized, and the way we're redrawing the entire graph every frame is particularly slow. In addition to fixing the way we draw the graph lines, we might consider using Godot's custom monitor features to see if it's faster than our roll your own code. Performance isn't the only problem. Another gap I know exists revolves around the way we're merging objects and writing to the output buffers in the shader. Because we aren't following parallel programming best practices, we sometimes end up writing to multiple places during the pairwise comparisons. This has the potential for us to accidentally wipe out our values or pixels, depending on the size and number of workgroups running. One way we can see this manifest is by checking the total mass in the system during each frame. We should expect it to remain constant, but we actually see the mass fluctuate and drop. There are some bugs involved, but this could be related to workgroups interacting with each other during collisions. If you have other ideas on how to handle merging, I'd love to hear your thoughts. The last consideration is something that's been on my mind recently on this and other projects. That's the fact that I'm not using Godot's recommended coding and formatting style guidelines for GDScript. Naming things is hard, and I come from a background where I'm using many languages at the same time, so my style is very fluid, and often crosses from other guidelines. I'm not sure if I'll go back and retroactively refactor those older projects, but moving forward I'm going to try to follow the guidelines as much as possible, especially for our videos. If there's interest, I might even put together a video on those guidelines, what they mean, and if you should or shouldn't consider them hard requirements for your games. What are your thoughts on style and design standards for Godot? If you made it this far in the video, then good on you. I learned a ton of new things and hopefully you did too. We can now use an OpenGL compute shader that runs over multiple passes. We learned how to use subviewports in Godot, how to rasterize circles in a shader, how to use Newton's principles for calculating n-body gravity, how to detect and resolve basic circle collisions, and finally how we can monitor the performance and specific pieces of our shader demo. All of these techniques can be applied in many ways in your games and fit nicely into our game dev toolbox. The code for the project is already live on GitHub, and if you haven't already, you can download it and change and experiment with it however you want. If you run into problems or have questions, you can revisit those parts of this video or drop us a comment on the channel. Looking forward to hearing from you, and thanks for watching the Pathfinder's Codex.